one of the most important things from day 6, guys, was page 3. This had actually a practice free response problem that is going to be just like part 3 of your test this Thursday. If you want to know what your last problem on your test is going to look like, it's going to look like this with expected value. Now, this is actually, if you know how to do it, this is very, very straightforward. Expected value is all about finding out what the probability of events is going to be, and then adding those events together, or adding those probabilities together when you're given a certain situation. What's the chances you bought at least 2 tickets? Oh, that means I take the probability of buying 2, add it with the probability of buying 3, and add it with the probability of buying 4. What are the chances that I bought more than 2 tickets? That would just be the probability that I bought 3 or the probability that I bought 4. So I add those 2 together. Really, the only tricky part of this is finding the expected value. Unfortunately, some of us may not know what that means. Get it, mean? Expected value, mean? Never mind. To find the expected value, you multiply your event with your probability and add them all together. So you just take each event, multiply it by the probability, and add it all together. So for a Jolly Rancher, can I get somebody to help me out with our first homework problem? In my opinion, probably the toughest one. You're a real man or woman if you can help me out with homework problem number 1 here. You got to find the vertex when we're given standard form. Frick. Isabella, you want to give it a shot? Thank you. So what's A, B, and C, Isabella? Yep. And why is it kind of important to label those? Yeah, it helps us find our vertex, the x of our vertex. What is that equation, Isabella, to find the x? Yep, negative b over 2a. So if we want to find the x of our vertex, it's actually a really simple math fraction. Plug in 36 for b over 2 times a, which is 3. And Isabella, what'd you end up getting for the x of our vertex when you plug that in? Negative 6. Let's go. Oh, what are some questions you guys maybe have as to how she was able to get that? Negative 6 for x. Anything kind of bothering you guys a little bit on that? How she got it? Okay, here comes kind of the trickier part. Isabella, now that we have x, how do we find the y of our vertex? Yep, input, output. If this is our input, we're going to plug this in for x and find out what the y is, what the output is. And I'm actually going to let you guys, if you haven't already done this, I'm going to let you go ahead and do it. So let's all pause for a second. And if you have not already done this, I'm going to give you a chance to do it. And if you have a calculator, guys, just plug this all in at once. You don't have to do each individual step. Plug it all in. Just don't forget parentheses. Isabella, what'd you end up getting for that?
For y?
Yeah. Negative 100 and what? I'm not saying that's, wait a minute. Check it out. So 3 times parentheses negative 6 squared plus 36 times negative 6 minus 7. I can type that in all at once. Negative 115, absolutely. You got to say that with confidence, Isabella. Great job. And so that's the y. Here you go. Oh, sorry. To be fair, I feel like that was a pretty good throw. So that's our vertex, guys. Thank you very much, Isabel. How about for one that's maybe a little bit more, has more parts, but is, I think, a little bit simpler. Anybody want to help me out with number 2? Oh, come on. I know somebody wants a Jolly Rancher. Hopefully, maybe. Jack, you want to help me out with number 2? Thank you, man. So, good news. What form is the second problem in right now? Yes. That means we can kind of just pick out the vertex. What's that looking like right now, man? I like the 8. Yep, x minus 8, so 8, and then negative 10. There you go. Yep, 8, negative 10. Nice job, Mr. Jack. Now, what would our new vertex be, man, if we were to translate 5 units right and 7 units down? So in other words, we're adding 5 to our x-coordinate, and we're subtracting 7 from our y-coordinate. So go ahead, Jack. What are you thinking, man?
13.
Yep.
Negative 17.
Yes, sir. That's some good mental math right there, man. That's some real good mental math. 13, negative 17 would be our new vertex. Add 5 to 8. Subtract 7 from negative 10. Here comes kind of the only tricky part, Jack. If we want to find the y-intercept, what do we got to plug in for x?
0.
Yes. So you plug 0 in for x to find the y-intercept. And we know negative parentheses 0 minus 8 squared minus 10.
Yeah.
And if you haven't already found that, I'll give you guys a second to do that. Remember, 0 minus 8 is just going to be negative 8. And then, oh, Ethan, do you need a jacket for, by the way, man? Physical code? Oh, gotcha. I couldn't remember if I got you one before you were gone or not. So what'd you end up getting, Jack?
0, negative 74.
Yep. You get 64, put a negative with it because there's a negative on the outside, minus 10, negative 74. So 0, negative 74. Nice work, man. We're 2 for 2 right now. How about the last one? This one's pretty easy. Because there's a negative out front, do we have a graph that reminds me of, I don't know. This isn't a class that I can poke fun at somebody for not liking because I actually like everybody. In my 7th period, I always joke with Jordan. I'm always like, the frowny face graphs remind me of you, Jordan. I always call those Jordans. He's a sophomore. I forget his name. No, Phelps. Yeah. But I always joke with him because there's a negative out front. Will we have a I don't know, a Chandler or a Jack? We're gonna have a Jack. That's right. It's a max. Our vertex is going to be at the top of this graph. And where's its value going to be at? Y equals negative 10. Oh, well, hey, Ethan just wants to contribute. My man's been gone for a while. And Ethan, where'd you get that from? Didn't that come from the y of our vertex? Max or min always comes from the y, just like the axis of symmetry always comes from the x. Okay. Anybody need me to leave that up there? I'll leave it up there for a second. And actually, you know what I'm going to do? I'm going to split today up. Before we jump into day 7, I'm going to give you guys a chance to work on. Thank you for not letting me forget. How about Jacob? Help me out, man. What are we going to be looking at real quick today on day 7, part 1?
What are we going to look at?
Yeah, what's our topic going to be, man?
Symmetry and graphical lines.
Hey, we saw symmetry earlier. Christian, what part of this chapter earlier did we see symmetry on? Went back to parabolas. One cut right through the vertex. Didn't they have a... Yeah, they had an axis of symmetry. So, hey, think back to that, guys. Something kind of similar. We know symmetry is whenever we have kind of a reflection that maps a figure onto itself. If something does not have symmetry, it's known as being, well, put an A in front of it. That's the beautiful English language. Asymmetrical. So I'm going to give you guys, I'm not going to read to you. Take about 20 seconds, guys. Really focus in on these 3 check marks right here. This is going to be the whole crux of today, these 3 check marks. So I'm going to give you some time here. Not super complicated, but if you don't know it, it's going to be really confusing. All right. So, David, When does a figure have symmetry? If there exists what?
It's just the rigid.
AKA, what are the four main ones we've talked about this chapter?
Reflection, translation, rotation, and slide.
Yeah. So those are kind of the big four there. So if a figure is in a plane, has line symmetry, it can be mapped onto Dakota. How can we map a figure onto itself? What do we call that? A line of symmetry, yeah. We can flip it over this line that creates symmetry between the two pieces. We flip it over that line. And so, guys, what we're going to do, this is going to be kind of a chill activity here. I want you guys to look. Tell me yes or no whether these 6 have a line of symmetry. And if yes, go ahead and draw those and state how many there are. I just kind of want to see how good we are as artists here. See if you guys can say yes or no, these shapes have lines of symmetry. And if they do, maybe draw them out. Hopefully do this in pencil. Don't do this in pen. RIP. No, check it out. Look at the Batman symbol here. Iconic. How can we create a symmetry here? Where can we draw a line? Right down the middle. Yep. So, hey, this has a line of symmetry. It exists. Is there anywhere else you could draw a line of symmetry that would be symmetrical? Well, now, wait a minute. If you do it on the sides, would the left side be the same as the right side? No. Is there anywhere else? No. There's only one line of symmetry here, guys. There's only one line of symmetry. Yep, only one. And so that's what we're doing here, guys. We're going through saying, okay, how many times could I split this thing into halves that would be the same? I'll give you a hint. I think there should only be one in here that does not have a line of symmetry. Only one that won't have any lines. In my opinion, the trickiest one, number 2. How about let's go, Bree, how many lines of symmetry do you think number 2's got here? Or you can kind of tell us where they are.
One's right down the middle.
Okay.
One is vertical.
So
Or not vertical,
horizontal. Okay.
I don't know if there's any one because it's kind of like reflective, Is it?
I gotcha. Could we say maybe that there is one diagonal?
No.
Why not, Jack?
Because the lines are on different sides.
Yep.
and you cut it in half.
Mm-hmm. So we got one down the middle, one to the left, and Jack's saying that if we tried to turn it, these lines are not lined up to where they're reflective of each other. I like it. So how many was that, Bree? 2. How about number 3? Let's go, Lucas. How many are you thinking on number 3, man? Lines of symmetry. Where would that be?
Right down the middle.
Okay, you thinking that's it? We're bisecting Patrick Star here.
Yeah.
Now wait a minute. I think there's another one. What would happen, guys, if I turned the shape like that? Couldn't we now split this right down the middle? There's 5. Yeah, there's one for each prong. One there. One there. One there.
You said that before that. He makes sense.
Yeah. He has a ton. Every single one of his edges, you could draw a line down to create kind of a new starfish, depending on how you turn it. There. You can do that for all 5 of those. Absolutely. How about number 4? Let's go. Kate, I thought you were raising your hand. I bet you can do it anyway. How many are you thinking, Kate? Because there for sure is. I know we all know that. Where are you seeing these 2 at, Kate? Yep, vertically. Those are definitely 2. Oh, wow. Look at that line. Beautiful. You can tell I'm an artist. Okay. How about what would happen, Kate, if I turned this diagonally? Do I now have an X that I could split perfectly? Yeah, so that would be 1. And how many of those could I do? Here and... Yeah, I could do the other one. So how many is that total? Yes, ma'am. We got 4. Nice work. How about number 5? Don't overthink this one, guys.
Go straight down the.
Straight down the middle, Jacob saying. So that's a yes. Are there any others?
And you go across, but
We couldn't go across because then we have a point at the top and flat on the other side. So can't go across. Couldn't go that way because that and that won't be the same. Couldn't go that way because that and that won't be the same. Are there any others? No, there's just one. And of course, some of you guys are probably about process of elimination. You know. What do we know in then, Taya? Will number 6 have a line of symmetry? Nope, it's parallelogram. No way to create symmetry with a parallelogram like that. Nice work, guys. So the last thing today, and we are done. I'm going to turn you guys loose. This is going to be really the only part of this day today that we're going to use some math on. But it's also going to be a little bit complicated if you don't get a chance to read it and understand it. So I'm going to give you guys, let's actually take about a minute. I do not want to rush you. We're going to talk about rotational symmetry. This is how you can map a figure onto itself. So in other words, you can take a shape, turn it a certain way, and it becomes the same shape again. So like think of an S. You turn an S 180 degrees, it's an S again. So a rotational symmetry is between 0 and 360 degrees. How many times can we map a figure onto itself where it becomes itself again before we get back to what it was originally? So take some time. We call it how we rotated that little origin. We call that the center of symmetry. I'm going to give you guys some time here to just kind of read over. There's a lot to process here. So go ahead. Big thing here. Kenzie, when we talk about order of symmetry, would you care to give us just a quick recap? What is the order of symmetry here in our first check mark? So let's help each other out here. Look at this shape up top. If we were to rotate that 360 degrees, how many times would it actually map and become itself again? You rotate it, you rotate it once, 90 degrees, it becomes itself. You rotate it again, 180, 270, 360. That would happen every 90 degrees. It would become itself again. You guys are all over that. So what would we say the order is? How many times was that? 1, 2, 3, 4. So we would say the order of symmetry is 4. That's how many times it can rotate back on itself before we go all the way around. How about magnitude? How do you find the magnitude, Jack? You take 360 and we divide it by, so we take 360 divided by 4. How many degrees would our magnitude be? 90, which is what they have up here for us. You take 360, divide that by 4, and that gives you 90 degrees, which is what we saw here. That's how many times we can rotate this shape onto itself, how far we have to rotate it. That would be our magnitude. So let's do 1 together, and then I'm going to let you guys finish the day by doing these last 2, and we'll check them. Let's do number 1 together, guys. Big thing. We got 3 things we got to do here. First, state whether it has rotational symmetry. Hunter, do you think this S is going to have rotational symmetry? Oh, yeah. In fact, it may be more than once. So we're going to say yes. It absolutely can rotate onto itself. Here's the thing, Hunter. Let's go order. Order in the court. How many times could we rotate this thing before it makes it all the way 360 back? Say it again. Twice, yeah. Could we flip this thing all the way around 180? And then again 360? Yeah. 2 times. So we could go 180 and then 180 would flip it back. Yeah. Way to go, Hunter. So order is 2 times that it maps itself. And did Hunter just give us the magnitude? What's 360 divided by 2? 180. He just gave us the magnitude. Yep. We know it's going to rotate onto itself 2 times. So you take 360 degrees divided by 2. The magnitude's going to be 180. That was quick. Those are our three things. So what I'm going to let you guys do, take some time, see if you can do 2 and 3. And I will put these answers up here shortly and let you check those. Kind of something similar here. You can go ahead and kind of look up as you're working. Number 2, looks like we can turn this thing 8 times and map it onto itself. So you take 360 divided by 8, that gives us a magnitude of 45 degrees. Number 3, there's 7 points. 1, 2, 3, 4, 5, 6, 7. That means you can rotate this thing onto itself 7 different times, I believe. Maybe, actually, did I do that wrong? 1, 2, 3, 4, 5, 6, 7. No, I'm good on that. So magnitude is 360 divided by 7. I got 51.4 degrees. 360 divided by 7 give you 51.4 degrees there.